Thank you, Violet, for the introduction. Hi, everyone. I'm Leonidas Kosmidis from Barcelona Supercomputing Center. I'm leading researcher there, and I've been coordinating the METASAT project. Last year, I presented the RISC-V platform that we built for the project. And this year, I will be talking more about the final project demonstrator that runs on top of this platform. But before we start, let me say a couple of words about our project. It was a 2-year research project funded by the European Commission. It ended in December, and it focused on low TRL. So we were focusing on having a demonstration of innovative space technologies validated in a representative laboratory environment. We were five partners in total. BSc, we were the coordinators of the project. We provided the hardware design, the low-level, the system software, and the high-performance use cases. We had Fentis that provided the space-qualified hypervisor, Ikerlan that worked on the model-based design, Collins Aerospace provided support for the digital twin, and we had also OHB that provided the high criticality space use cases and made also the final integration of the project. The motivation of our project was that nowadays we require high level of very high degrees of performance in future space missions that cannot be provided by existing space processors. So we need more capable space processors like the ones that we developed in this project, or the HPC and the GR765 that we will hear later this week. The type of software that we need to run is artificial intelligence, because we need a high level of autonomy. We need to process high resolution data, and more importantly, we need to process them on board. We don't want to send them to the Earth. This requires more complex hardware and more complex software compared to what we are using currently in space systems. For hardware, we require complex multi-cores, GPUs, and AI accelerators. And in the software side, we need truly parallel CPU and GPU software. Traditionally, for space systems, for institutional missions, we rely on space-grade processors and space-grade FPGAs. We have many different subsystems, and each of the subsystems is implemented in different hardware and uses different software. Sometimes this is they have different criticalities, and sometimes they are bare metal or use a qualified real-time operating system like Artemis. Our approach in the project was, instead of using a lot of distributed hardware, to use a single, complex, highly capable space processor system on chip and integrate multiple functionalities on it, similar to the integrated modular avionics concept that is used in aviation. This results in lower hardware cost.
Sorry to interrupt you. It
Yep.
looks like we're sharing the wrong screen on here. Do you mind if I take a... All right, there we go. Oh. There we go. Sorry about that, folks.
No worries. So also regarding software, by the use of time and space partitioning, we're able to use software of different criticalities without need to qualify them to the highest criticality level. And this results also to lower software qualification cost. And also we leverage model-based design in order to manage the complexity of the platform. Since at the moment we started the project, there was no hardware with this complexity, apart from a couple of COTS devices. We decided to build our own hardware platform based on the RISC-V ISA. So here you can see how it looks like. We have a multi-core based on the Geissler Noel 5 that was integrated with the Sparrow short vector AI accelerator unit that we developed at BSc. and it's connected to a RISC-V GPU, which is
Give me mute access. All right, testing, 1, 2, 3. Does it look good on Zoom? All right, we're back. Thank you, Leonidas.
Thank you. So we continue with part 3 of presentation, or no?
I guess I'm not sharing. Everybody saw me do this. All right, can we check audio? All right, thank you. So sorry about that, Leonidas. Yeah, we're sweet. Thank you.
And here you can see the resource table. You can see some of our partitions are really big, 256 megabytes. So this is like an indication of how powerful our platform is that can integrate so many different partitions with a lot of resource needs. Now we'll talk individually about the different use cases. I will start with the instrument control use case. So for the instrument control unit, mainly we had two functionalities. The first one was processing of instrument data. So reading housekeeping data, providing them to ground for via telemetry, and also steering the hardware. Also, we had the interlock and failure detection. In this case, if something was detected to be wrong in the system, the interlock would take over and also provide an alert for this abnormal condition. The instrument control software was a fork from a project in OHB. It was ported to RISC-V. It was added telecommand and telemetry in push, and also networking connectivity in order to communicate with FDIR and interlock software partitions. Now I will talk a bit more about the interlocks use cases. In space systems, we care a lot about the overall system dependability and safety. And one of the ways to implement this is by redundancy. And in the particular case, we used dissimilar redundancy. So the idea here is that we have the instrument control software, and then we have a complete independent module that is monitoring the software, and if something wrong happens, it takes over. Usually, this is implemented in hardware in past projects at OHB, but this has some limitations. First of all, we can only monitor simple conditions. It adds extra resource budgets, so we need a bigger FPGA to implement more and more interlocks. It's very inflexible if we want to modify the interlocks during the project development, and even more problematic if the operating system, the operating conditions during the missions change and we want to update it. And finally, this has a high cost because of the qualification cost of the hardware. So the idea in this project was to move this to software. So we had a more complicated, more sophisticated instrument control software that OHB is interested to qualify for a medium criticality level, like category C, in order to keep the costs down. And at the same moment, we have another interlock software module this time that can monitor this condition and take over if something wrong happens. In this case, we care about this software interlock to be as simple as possible, so bare metal and small amount of software. And that will be qualified to one criticality level higher. In this particular case, criticality B according to ECSS. So in this way, we can achieve a higher flexibility and significantly lower effort for qualification compared to if we were qualifying everything up to criticality B. Here you can see how it looks like the first type of interlocks that we had. In this case, we were implementing a simple traditional interlock based on a threshold, particularly for temperature. And whenever the temperature was raising more than the threshold, then the hypervisor was using this new functionality that we implemented in the hypervisor in order to block the instrument control software from directly controlling the hardware. We modeled this in our test environment regarding the inter-partition communication. We modeled it also the functionality in Simulink, and we verified it with Simulink testing. And then we generated code and integrated together with the different libraries that we had for communication with the telemetry and for the UART control. Here you can see how our screen looked like. Here we had the output of the partitions, and for the beginning of the execution, we were running with nominal conditions, and then we forced a higher value than the threshold, and this indicated that the access to the device was blocked by the operating system, and we achieved what we wanted. The different type of interlock that we used was more complicated, and in this case was protecting a device like a flash device from excessive writing that could damage the device. So in this case, we had to monitor frequency of writes, and whenever in a single period we were exceeding a certain limit, we had to block writes to the flash device. We have used the same method as before. Here you can see that for the periods when we have small writes, it's everything is okay. But whenever we exceed a limit of the frequency of writes, then the interlock software intervened and blocked the access. Now we'll talk about the FDIR AI use case. In traditional FDIR, we can only use threshold decisions, or we rely on the human operator on the ground to detect something wrong and respond to this. In Metasat, we implemented an AI-based FDIR that can find more complex interactions between different sensors. It's based on neural networks and an autoencoder, and it makes predictions based on the last 1 hour of readings. It calculates an anomaly score, and whenever this raises over a threshold, then it creates an alert. Here you can see how we predict and the actual measured values, and the anomaly score actually computes what is the difference between the two. The software is also integrated with the method that receives the housekeeping data and provides the anomaly detection status to the instrument control software. And here you can see also how it looks like. In the beginning, we have nominal conditions, but then at some point we start injecting some anomalies, and this is detected and provided to the instrument control software. Now we'll talk about the high performance use cases. First, we had the cloud screening use case. Here we were detecting the coverage of images from clouds, from satellite images. we have used we have imported pre-trained neural networks in MATLAB and Simulink. We have used that for validation, and then we use the capability of MATLAB and Simulink to generate TensorFlow-like code. However, in our qualifiable software stack, we only provided support for TensorFlow Micro. So we have created a converter from TensorFlow Lite to TensorFlow Micro, and we were able to accelerate this either with our AI accelerator or with Vortex. So here we have a code generation that is specific for AI, but also we wanted to be able to support GPU execution of general purpose code. So MATLAB and Simulink is able to generate also CUDA code, but our GPU does not support CUDA. So we had to transform this code automatically with some source-to-source translators that we have built to qualifiable software, GPU software stacks that allow us to execute model-based design code in our GPU for general purpose computations. For the integration, we have created three different versions of our partitions. We had a non-accelerated version that was running on the CPU, one version that was accelerated with Sparrow, and one version that was accelerated with the GPU. And all these partitions, they implement the same API. They only differ on the backend of TensorFlow Micro that they were linked with. So it was very easy to change from one partition to another in order to perform detailed experiments for measuring the performance of our platform. The integration was performed by OHB, and as I mentioned, it was seamless. When we were putting two partitions that were using the GPU, they were able to coordinate automatically with our GPU I/O server. We have evaluated different things with our demonstrator. First of all, what was the impact of the real-time operating system or the hypervisor? And we confirmed that this was negligible. And whenever we were running the Sparrow accelerated version, we achieved 2 times speedup compared to the scalar version. However, for the GPU, we didn't get the performance we expected because we have used a small configuration. We just configured the GPU with a single compute unit and 4 threads just for the demonstration of the concept. And we have also non-optimized hardware and software. But for us, performance at this stage was not important. We were more interested in having a fully functional hardware and software setup. And with improvements in the near future, we think that we can get similar performance with what we can get with COTS GPUs. For the SIP detection, we were able to locate vessels on satellite images. And again, we have used the same flow as I mentioned before. We have evaluated again the overhead for the operating system and from the hypervisor, again, was negligible. And in terms of acceleration, we were able to get 2.5 times speed up with our acceleration unit compared to the scalar version. And similarly, for the performance of the GPU, it was not that high. We have also evaluated the case in which we were having the 2 high-performance use cases sharing the accelerator or the GPU. So here we could find what was the best combination of which use case was better to be executed on the accelerator or on the GPU, but also to demonstrate that when we had 2 partitions using the GPU, we were able to do so. So to conclude this demo, we have demonstrated that we have built a high-performance RISC-V prototype platform on an FPGA with a qualifiable software stack. We were able to have multiple use cases executed in parallel, and they had different criticalities. We achieved significant acceleration and also important savings in hardware and software cost. And just to give you an idea of future work, first of all, we are cleaning up our hardware and software, and it will be released as open source. We will contribute our code to ESA's OBBMarkML repository, and the platform will be used also in other European funded projects to improve the features and the performance, like the Smarty Horizon Europe project. And with that, I conclude my presentation. I will be happy to take questions.
Thank you, Leonidas. Any questions? Questions?
Hi, how's it going? My name is Ty. I'm from Firefly Aerospace. I was wondering if you could talk a little bit just about the AI implementation of your fitter and perhaps like, an example of what fitters you use. Was it just like, turning off and on a sensor, recalibrating a sensor, stuff like that? So
for the implementation of the model, as I mentioned, we used 21 different temperatures from different subsystems of the satellite. And the interesting thing here is that, temperatures are not isolated. There are correlations between them because if two sensors are located close with one another, maybe one affects the other. So we have trained based on that, and we were able to detect some correlations like that. Thank you.
Hello. Have you tried this in a radiation environment?
No, that was only in a laboratory setting, and we were also using the GPL version of Noel 5, so not the fault-tolerant one. But in the future, we are planning also to have, yes, radiation, actually a fault-tolerant version of the CPU, and also we are working on a fault-tolerant version of the GPU.
Hi. The RISC-V encompasses a large number of different kinds of processors. What kind of family or what were you actually targeting when you were building this?
So on the CPU side, we have used the most complex configuration from Noel 5. If you're aware, Noel 5, it's quite configurable. So we have used the one that the one that Geisler terms as high performance. So it includes the hypervisor. It's 64-bit and it has a memory management unit. So it has all the features. And the GPU has similar support. So it's the 64-bit ISA of RISC-V, but we don't have a memory management unit there. It's something that we plan to support in the future.
Hi, I had a quick question. Sorry. So I play a lot with the Google Coral TPUs and a few other ones, but I was curious about the ones that you guys are using. Do you have parts that can support like LSTM type architectures, or are you guys strictly in like convolutional architectures and just simple, fully connected stuff and things like that?
Yeah, actually, this Sparrow unit, it's hardware and software co-designed specifically for inference of convolutional neural networks and for fully connected.
Okay, so none of that like LSTM.
No, it's a custom design, and the interesting thing is that it's very low cost. It reuses the integer register file, so yeah, it can provide high acceleration with low hardware cost. Thank you.
Okay, we take one more question, and that's it.
Hi, my name is Derek Johnson from Rocket Lab. Question I had on AI and fitter is how do you bound fitter? Because the R in fitter is response, right? And some responses are really minor and not that significant. Some responses are critical and can completely change the behavior of the vehicle. So how do you kind of bound that and prevent AI from kind of going off the rails?
That's a very good question. So actually here we played safe and we tried to be in line with the handbook of ESA on the use of AI that was published as a draft last year and was open for comments. So here we are in the first stage of adopting AI in space. So actually we have the redundancy that I mentioned before. So we have the interlock, and here we only perform the detection. And if something goes wrong, we have also the traditional interlock that it will intervene and will protect our system. So we didn't go beyond that.
Thank
Thank
you,
you.
Leonidas. Let's
Thank you.
give it up.